Hello everybody. The topic of today's class is reaction intermediates. I'll be dealing with the generation, structure and stability of carbocations, carbanions and free radicals. Before that, we have to see what you mean by reaction intermediate. These are the intermediate species formed and utilized during the stepwise progress of a reaction. These are formed and they are getting utilized in a reaction. And they exist only for a very short period of time and they are highly reactive. They could be cations, anions or neutral species. Or as they do not live long, it's not possible for them to isolate. Only the most stable ones could be isolated so far. Only one or two, a very few reaction intermediates have been isolated and studied separately, but normally they are not at all. It's impossible to isolate them. Typical reaction intermediates are the most important ones are carbocations, carbanions and free radicals. The first one is carbocations. Definition is just simple definition, that is organic ions which contain a positively charged carbon atom are called carbocations. Okay, then since the positively charged center has only 6 valence electrons, it is electron deficient. It's a cation. From there itself we can understand that it is electron deficient. R plus, normally we can represent it as R plus. And it has since it is electron deficient, it can act as a Lewis acid and it can accept an electron pair very much easily to complete its octet. Therefore, it's very much short-lived and this is highly reactive. And here I have shown the bond shift. The bonding pair is shifted towards this Z and Z will be more electronegative than carbon normally. In such cases, carbocations are formed. Here are some examples. This is methyl carbocation, first one. The second one is ethyl carbocation because it is derived from ethane. Methyl carbocation is obtained by the removal of one hydrogen from methane. Methane is CH4, and if you are removing one hydrogen, one H minus from there, you will be getting methyl carbocation, CH3 plus. And from ethane, you will be getting ethyl carbocation. And the third one, these are the most common carbocations that we are dealing with. That's why you have to know its name. This is isopropyl carbocation, and this one is tertiary butyl carbocation. All these three are alkyl carbocations. And this is allyl carbocation. This one is allyl carbocation, and the last one is benzyl. And you should note another point that here this ethyl carbocation is called a primary carbocation because the carbon carrying positive charge is directly connected to one carbon atom. That's why ethyl carbocation is an example of a primary carbocation. Like the same, isopropyl carbocation is an example of a secondary carbocation because you can see that carbon carrying positive charge is directly connected to two other carbon atoms. And this tertiary butyl carbocation is an example of a tertiary carbocation. Okay. And now we have to see the formation. How are they formed? Two simple methods I have shown here. I have given here. One is by ionization of an alkyl halide. Rx, you know that this halides are more electronegative than carbon. So normally, naturally, the bond will be shifted towards the halogen part and you will be getting the R plus. For example, methyl chloride. From methyl chloride, we will be getting methyl carbocation. And the second one is protonation of alkene. This one we have seen in the case of electromeric effect as the example of while we were discussing about the applications of electromeric effect, we have seen this one. Alkene plus a proton will give you corresponding carbocation. Now hybridization and structure. The positively charged carbon atom is sp2 hybridized. The positively charged carbon in a carbocation is sp2 hybridized. sp2 hybridization means there will be 3 sp2 orbitals. Those orbitals will be planar and the bond angle between them is 120 degree, right? Bond angle is 120 degree and there will be 3 sp2 orbitals with single electrons. Okay, so that the carbon can form sigma bonds with 3 other atoms or groups. And there will be, in the case of sp2, there will be an unhybridized pz orbital that is shown in the pink color. And here one thing to be noted, the difference is that this p orbital is vacant. Okay, the unhybridized pz orbital is vacant, there is no electron. Normally in the case of sp2 hybridization of carbon, there will be one single electron residing on the unhybridized pz orbital. But here in the case of carbocation, that is vacant. And the shape is planar triangular and the bond angle is 120 degrees. So regarding the hybridization and structure, it is the carbon atom, the carbon carrying positive charges sp2 hybridized and the unhybridized, so that the 3 sp2 lobes can form sigma bonds with 3 other atoms or groups. And the unhybridized pz orbital, which is in a perpendicular plane direction, is empty. Okay. And regarding the stability is normally determined by its structure. Okay. And the simple alkyl carbocations, the stability is found to be tertiary is the most stable, then comes secondary, and then comes primary, and last one is methyl. Okay. Then the stability increases as the number of hypoconjugative structures increases. Here stability is determined by two factors. One is hyperconjugation and the other is inductive effect. And here in the case of this tertiary carbocation, there will be, for example, in the case of tertiary methyl carbocation, if you are taking CH3 3 times C plus tertiary butyl carbocation, the number of hypoconjugative structures will be 9. This one we have discussed in the case of hyperconjugation, and I have given the detailed explanation over there. Please check back. And this one, in the case of secondary, if you are taking isopropyl carbocation, normally isopropyl is taken CH3 twice CH plus. In the case of isopropyl carbocation, there are 6 hypoconjugative structures. In the case of ethyl carbocation, CH3 CH2 plus, there will be 3 hypoconjugative structures, and this methyl carbocation is not having any effect, any hypoconjugation. It's not possible. Hypoconjugation is not possible in the case of methyl carbocation. So based on the number of hypoconjugative structures, tertiary will be having more number of structures, then comes secondary, then comes primary, and methyl is not having any kind of hypoconjugative effect. And we can explain the same thing using the inductive effect also. Because since the carbocation is positively charged, any effect, anything which decreases the positive charge density on that carbon atom will be a stable condition. Okay, here positive charge density has to be minimized as far as possible. For that, this alkyl groups are having inductive effect, and here in the case of methyl carbocation, there is no alkyl group, and here in the case of primary carbocation, there is an alkyl group. So it will be pushing its electron density towards the carbon carrying positive charge, and thereby minimizing the electron positive charge density on that carbon to some extent. Okay, and in the case of secondary carbocation, there are 2 plus I effect groups, and both of them can contribute towards this carbon cation. Both of them will be pushing its electron density towards the carbon carrying positive charge, and the electron deficiency is somewhat managed. Okay, and here in the case of tertiary carbocation, there are 3 groups, and they are all these 3 will be donating its electron densities. One part of its electron density is contributed to this carbon carrying positive charge, and it is getting stabilized. Okay, appo positive etra korayunno atrayum stability aanennu paranju. Appo electron density mottham endu cheyunu, in the case of tertiary 3 alkyl groups undu, ellarum avarude oru electron density ude oru part endu cheyunu carbon nekku donate cheyunu. അപ്പോൾ പോസിറ്റീവ് ചാർജിന്റെ ഡെൻസിറ്റി കുറച്ച് ഇലക്ട്രോൺ ഡെൻസിറ്റി കിട്ടുമ്പോൾ പോസിറ്റീവ് ചാർജിന്റെ ഡെൻസിറ്റി എന്ത് ചെയ്യും, കുറയും. അപ്പോൾ അങ്ങനെയാണ് ഇത് സ്റ്റെബിലൈസ്ഡ് ആവുന്നത്. അപ്പോൾ വി ക്യാൻ എക്സ്പ്ലെയിൻ ദ സ്റ്റെബിലിറ്റി by using both the factors of both the concepts of hyperconjugation and plus the effect of alkyl group. And here in the case of allyl and benzyl carbocation, this is allyl carbocation, this is resonance stabilized. അപ്പോൾ ഈ പറഞ്ഞ ഇൻഡക്റ്റീവ് ഇഫക്റ്റ് ആൻഡ് ഹൈപ്പോകോൺജുഗേറ്റീവ് ഇഫക്റ്റിനെക്കാളും കൂടുതൽ stronger effect ആണ് the resonance effect എന്ന് പറയുന്നത്. As the number of resonance effect increases, or if the carbocation is resonance stabilized, that will be more stable when compared to the normal alkyl carbocations. So in the case of allyl carbocation, we can show the resonance like this. There are two resonance structures in the case of allyl carbocation. I'll write it here, CH2 plus CH double bond CH2. Okay, since it is resonance stabilized, it is stable. And in the case of benzyl carbocations, there are 5 resonance structures possible. Here is the resonance canonical structures. Okay, the first one will be this one, and it will move on like that, like this. Carbon carrying positive charge. This was our center actually. Okay, even positive charge this is that much stabilized. This benzyl carbocation is all the more stabilized. And benzyl carbocation, now we have to see another order. This is benzyl C6H5. It's not pH. C6H5 CH2 and CH2 plus, and this is C6H5 CH plus C6H5, and then comes C6H5 C plus C6H5 C6H5. This is the first one is benzyl carbocation. The second one I have written is diphenyl methyl carbocation. This is triphenyl methyl carbocation. And now predict which will be more stable. If you are comparing these three, which will be more stable? Obviously this triphenyl methyl carbocation will be more stable. Then comes diphenyl methyl, then comes benzyl. Because in the case of benzyl carbocation, we have seen these 5 resonance structures could be seen, and if you are adding the number of this benzene ring, the number of resonance structures are becoming doubler. In the case of this one, there will be 10 resonance structures, and in the case of triphenyl methyl carbocation, there will be 15 resonance structures. Okay, therefore this becomes the most stable among these three. And another one to be discussed is tropylium cation. Tropylium cation എന്ന് പറയുന്നത് cycloheptatrienyl carbocation ആണ്. This is aromatic and this is so stable. This is very much stable so that it can be isolated and studied. Okay, in the introduction part I told you that it's not possible for them to be isolated, but since this tropylium cation is highly stabilized, this is isolated and studied separately. It's all about carbocations. Now comes the second one, free radicals. Okay, these are the atoms or groups having unpaired electrons. These are formed by homolysis. They are having unpaired electrons and they are formed by homolysis. And as usual, they are highly reactive and short-lived, but they are neutral. And they are paramagnetic in nature because of the presence of the unpaired electron. Here the bond shift is shown by, cleavage is shown by this fishhook arrow. Okay, and for this to happen, both the carbon and this Z part will be having almost comparable electronegativities normally. Formation, it's formed by homolysis. Other than type, it could be photochemical or thermal homolysis. So photochemical means in presence of light, H nu, and this chlorine is converted into 2 Cl radicals, and this is hydrogen peroxide. This is also cleaved into 2 OH dot radicals. And in the case of thermal homolysis, here N2 molecule is expelled and the remaining one is the 2 methyl radicals are obtained, and this is benzoyl group. Okay, here this is benzoyl peroxide, and here also oxygen molecule. The first one, for the first cleavage is this one. Sorry, not here. The first cleavage takes place here, and there are 2 portions are obtained, and then after that from here also the bond is cleaved like this, so that carbon dioxide molecule is expelled and we are getting C6H5 radical. And regarding the hybridization and structure, it is very much similar to that of the carbocations. This is also sp2 hybridized, and it's also the shape and hybridization is the same, planar triangular. and the bond angle is 120. There is only the difference in the fact that there is an unpaired electron present on the unhybridized pz orbital. In the case of carbocations, the pz orbital was empty, but here there is an electron. Okay, that is the only difference. All other things are the same as we have discussed in the case of carbocations. And regarding the stability, this one also follows the same trend of the carbocations. Tertiary is more stable, then comes secondary, and then comes primary. The reason is also the same, hyperconjugation and plus effect of alkyl groups. So the tertiary radical is having highest number of hyperconjugative structures, and it is the most stabilized by the plus effect of 3 alkyl groups. Okay, and in the case of methyl radical, there is no hyperconjugation and plus effect is playing here. So that is the least stable one. And when it comes to allyl radical, it also follows the same trend. Every time, whether it is allyl carbocation, carbanion on radical, or benzyl carbocation, carbanion or radical, they will be stabilized because of the resonance effect. So this is the stabilization of allyl and benzyl free radicals. So they are more stable than alkyl, their alkyl counterparts. And the third one and the last one is the carbanions. Organic ions which contain a negatively charged carbon atom are called carbanions. They are also highly reactive and short-lived. They are electron rich and therefore they are nucleophile by nature. Nucleophiles, and definitely if they are nucleophiles, they will be Lewis bases. And here the bond is shifted towards the carbon atom. Okay, to give you a carbanion. Formation is by heterolysis. From an alkene, if you are abstracting this hydrogen using a base, R minus will be obtained. And second one is by the decomposition of carboxylate ion. Carboxylate, this is the carboxylate ion. This is obtained from acetic acid. This could be obtained from acetic acid. Okay, and this one, so this is a acetate ion, and this acetate ion, it is decomposed to give you methyl carbanion and carbon dioxide gas. This will be expelled from the system. Carbon dioxide will be expelled from the system. And then the third one, it's not second, it's the third one. Okay, third example is by the decomposition of organometallics compound. This is Grignard reagent, methyl magnesium bromide, the simplest Grignard reagent obtained. And from here, the bond separation, the charge separation is naturally like this. Carbon will be having a negative charge, so CH3 minus will be obtained, and MgBr plus is the byproduct. Regarding the hybridization and structure, it is different from the other two. This is sp3 hybridized. Carbon carrying negative charge is sp3 hybridized. And the orbitals are arranged in a tetrahedral fashion. So there are 3 sp3 orbitals, and there are 4 sp3 orbitals, and it could be formed, and 3 bonds could be formed. Here it is shown like this. 3 bonds are formed, and in the 4th sp3 orbital there is a lone pair. This is just similar to that of the shape and hybridization of ammonia. So it's pyramidal shape. Normally it should have been tetrahedral because of in the case of methane is also sp3 hybridized, and there we know that the shape is tetrahedral. The orbitals are tetrahedrally arranged. Okay, this is the normal case of sp3 hybridization, and here will be hydrogen atoms will be coming and attaching. But here, what is the difference between the methane and this methyl carbocation is that here in this last lobe, in the 4th lobe, instead of 1 electron, there are 2 electrons present. Okay, 2 electrons means we will be depicting it as a lone pair. So 3 sigma bonds could be formed, and in the 4th one, in the 4th orbital, sp3 orbital, there are 2 electrons or 1 lone pair is present. And as a result, the normal bond angle of this sp3 hybridized carbon atom is 109 degree 28 minutes. But because of the presence of a lone pair over there, that lone pair will be crunching the other groups together. Okay, repulsive forces and down. Therefore, the bond angle is it's lower than the expected bond angle of 109 degree. It comes normally Okay, it depends upon other factors also. So instead of this normal bond angle of 109 degree 28 minute, it is normally between 97 and 100 degree. So depending upon the nature of the groups attached to it, there could be a change in bond angle. Or range ആണ് താഴോട്ടും പോവാം മുകളിലോട്ടും പോവാം. Bond angle ഒരു correct 109 degree 28 minute ആണെന്ന് പറയാൻ പറ്റില്ല. Normally എന്താ ഉണ്ടാവുക വെച്ചാൽ because of the repulsion ഇവർ അടുത്തേക്ക് വരിക ചെയ്യുക. Bond angle decrease ചെയ്യുവാണ് ചെയ്യുക. Okay. And another point, if the negatively charged carbon is bonded to an unsaturated system, the carbanion becomes sp2 hybridized. Okay. For example, in the case of an allyl system, CH2 double bond CH CH2 minus. Here, the carbon carrying negative charge is attached to an unsaturated system. So, in the case of this example, this carbon carrying negative charge is not sp3, but it is sp2. Okay. Now, stability, it is normally determined by structure, and here the trend is reversed. Here, primary carbanion becomes most stable, then comes secondary, and then comes tertiary. Okay, now the trend is reversed. Methyl is the most stable one, then comes primary, secondary, tertiary. With the reverse effect, we carbocation is stabilized down. Neutral try. Carbocation neutral electron density neutral neutral stabilized down. In the case of carbanion also, neutral stability. Okay, extra electron density disperse. Now, carbon electron density is more stable. Now, in the case of methyl carbanion, there are 3 hydrogen atoms. But in the case of this primary carbanion, 1 alkyl group is attached. Now, alkyl group effect it is plus I effect. It will be donating its electron density towards this carbon. Now, carbon already negative, but instead it is receiving more electron density from the groups attached. So, it is little bit destabilized. And in the case of secondary, it is receiving the same electron density from 2 methyl groups. That's so all the more destabilized. And in the case of tertiary, 3 plus I effects under already it has an electron density over there. It has to get rid of it, but it is still receiving electron density from the 3 groups attached. So that becomes it's the least stable one. Okay, just reverse. The trend is just the reverse as that of carbocations. And allyl and benzyl carbanions, they are stable. Allyl and benzyl will be more stable than their alkyl counterparts because of the resonance stabilization. Here is shown how it is resonance stabilized. And this is benzyl carbanion. As you can see, there are 5 resonance structures in the case of benzyl carbanion. So this is the most stable condition. And another point is stability of carbanions increases as the amount of S character increases. So this justifies the observed order of acidity of alkanes, alkenes and alkynes. This is shradhikkanam. Okay, alkyne is more acidic than alkene, then comes alkane. For example, alkyne acetylene, CH triple bond CH. Alkene ethylene edutha CH2 double bond CH2. Alkane is CH3 CH3. And now we are removing one hydrogen atom from all these 3, and you will be getting CH triple bond C minus. CH2 double bond CH minus. And from ethane you will be getting CH3 CH2 minus. Right. Now, are more acidic? This dissociation are more acidic. Now, dissociation pattern ion stability. Discuss HCl. HCl stable condition H plus and Cl minus. Now, dissociation easily. The same concept would apply. This is hydrogen കൊടുക്കുക എന്ന് പറഞ്ഞാൽ that depends upon the stability of the remaining species ion obtained. അതിനാണ് നമ്മൾ ഇവിടെ പറഞ്ഞിരിക്കുന്നത് എന്താണ് stability of carbanion increases as the S character increases. അപ്പോൾ ഇവിടെ നോക്കിയാൽ acetylene ആണ്, that is sp hybridized അല്ലെ, ഇവിടെ കാണിച്ചിരിക്കുന്ന കേസ് sp hybridized ആണ്. അപ്പോൾ this is sp hybridized. അപ്പോൾ percentage of S character എന്തായി 50% S character ഉണ്ട്. And in the case of ethane ethylene നമ്മൾ ഒന്ന് എടുത്തു, അപ്പോൾ ഇതാണ് കിട്ടുക. അപ്പോൾ this is sp2 hybridized, ethylene is sp2 hybridized. അപ്പോൾ എന്ത് വരും, 3 ലോബിൽ ഒരാളാണ് S എന്ന് പറയുന്നത്, അപ്പോൾ 1/3 into 100. അപ്പോൾ അത് എത്രയാണ് വരിക 33%, 33.3333% ആണ് വരിക. And in the case of sp3 percentage of S character എങ്ങനെയാ കാണാം, there is 1 S and total number is 4 അല്ലേ, അപ്പോൾ into 100 എത്ര 25% വരും. അപ്പോൾ പറയുന്നത് എന്താണ്, നെഗറ്റീവ് അയൺ is stabilized as the S character, percentage of S character increases. അപ്പോൾ in the case of acetylene അതൊരു ഹൈഡ്രജൻ പെട്ടെന്ന് കൊടുക്കും. എന്തുകൊണ്ടാണ്, the resultant carbanion is stabilized because of increased percentage of S character. Okay, അപ്പോൾ ഇല്ലെങ്കിൽ ജസ്റ്റ് ഇത് ഓർത്തു വെച്ചാലും മതി, എന്താണ്, as the percentage of S character increases the stability of carbanion increases. ഇത് നമ്മൾ അപ്ലൈ ചെയ്യുന്ന ഒരു പോയിന്റ് ആണ് ഇപ്പോൾ ഡിസ്കസ് ചെയ്തത്. acidity of alkanes and alkynes, if you are comparing, alkynes will be more acidic, then comes alkene, then comes alkanes. With this we are ending the discussion on reaction intermediates, carbocations, carbanions and radicals. Thanks for watching.